Imagine you are on a trip of a lifetime. It's April 1st, 2026, and you've just departed from Argentina on a Dutch-flagged cruise ship. You are one of 147 people on board, 88 passengers and 59 crew members, representing 23 different nationalities. Your itinerary takes you across the remote South Atlantic, but just days into the voyage, something goes wrong. On April 6th, an adult male passenger develops a fever, headache, and mild diarrhea. 5 days later, he is in severe respiratory distress and dies on the ship. No one knows why. His body is offloaded at St. Helena on April 24th. On the exact same day, a woman who was a close contact of his goes ashore with gastrointestinal symptoms. So she is evacuated on a flight to South Africa, but she deteriorates rapidly in the air and dies upon arriving at the emergency room on April 26th. Meanwhile, a third passenger, another adult male, visits the ship's doctor with a fever, shortness of breath, and signs of pneumonia. He is medically evacuated to an ICU in South Africa. And then, a fourth passenger, an adult female, falls ill on April 28th and dies on May 2nd. By May 2nd, the World Health Organization receives an urgent notification from the United Kingdom about a cluster of severe acute respiratory illness on the ship. The ship is currently stationed off the coast, with passengers confined to their cabins, practicing maximum physical distancing. Authorities launch a massive coordinated response. Extensive respiratory panels come back negative for common diseases. It wasn't until May 2nd that a laboratory at the National Institute for Communicable Diseases in South Africa finally confirmed the culprit using a PCR test. It was a hantavirus. Hantaviruses belong to a family Hantaviridae, and there are over 20 different viral species in the genus. They naturally infect small mammals, specifically rodents, where they cause long-term infections without making the animals sick. Depending on the specific rodent subfamily they infect, they cause different diseases in humans. Humans usually catch hantavirus by breathing in aerosolized dust contaminated with the urine, feces, or saliva of infected rodents, or occasionally through a rare rodent bite. This exposure often happens when people clean out infested, poorly ventilated spaces like barns or cabins, or during farming and forestry work. Once inside the human body, hantaviruses cause one of two devastating syndromes. The first is hantavirus pulmonary syndrome, or HPS. This is primarily found in the Americas. In North America, the main culprit is Sin nombre virus, carried by the deer mouse, while in South America, the Andes virus is the primary case. HPS is brutal. After an incubation period of 1 to 8 weeks, early symptoms kick in: fatigue, fever, muscle aches, especially in the thighs, hips, and back, headaches, chills, and stomach issues like nausea and diarrhea. But 4 to 10 days later, the late symptoms hit. Patients experience severe coughing, sudden respiratory distress, and their blood pressure plummets. Their lungs literally fill with fluid, causing a 38% fatality rate. Though in the Americas generally, the case fatality rate can reach up to 50%. The second syndrome is hemorrhagic fever and renal syndrome, or HFRS. This is primarily found in Europe and Asia, though the sole virus carried by the brown rat causes HFRS and is found worldwide. HFRS mainly attacks the kidneys and blood vessels. Symptoms hit suddenly within 1 to 2 weeks: intense back and abdominal pain, fever, blurred vision, and a flushed red face. In late stages, it causes internal bleeding, vascular leakage, shock, and acute kidney failure. The severity depends entirely on the virus strain. One virus strain carried by field mice have a 5 to 15% fatality rate, while the sole virus carried by voles are much milder, less than 1% fatality rate. Globally, there are roughly 10,000 to over 100,000 hantavirus infections each year, mostly in Asia and Europe. But despite how dangerous it is, human-to-human transmission is incredibly rare. The Andes virus has only ever been documented in South America, usually among close, prolonged contact with intimate partners. But to understand why this virus is so deadly, we have to look at what's happening at the nanoscopic scale. Hantavirus virions are tiny spherical particles measuring just 80 to 120 nanometers across. Their genetic code is essentially a 3-part instruction manual made of a single-stranded negative sense RNA separated into small s, medium m, and large L segments. The large segments code for the viral polymerase, an enzyme that copies the virus RNA. The medium segment creates 2 surface glycoproteins, G1 and G2. These proteins link together to form square-shaped spikes that stick out of the virus's lipid envelope. These spikes are the keys the virus uses to unlock human cells, specifically targeting cellular receptors called beta-3 integrins. Finally, the small segments create the nucleocapsid, or the N protein, which coats and protects the viral RNA from being destroyed by the cell's defenses. Once the virus attaches to a cell, it is swallowed up in the process called endocytosis. Inside, a drop in pH triggers the virus to fuse with the cell, releasing its genetic material into the cytoplasm. To start replicating, the virus uses a devious trick called cap snatching. The viral polymerase literally cuts the protective caps off of the host cell's own messenger RNA and uses them as primers to start building its own viral RNA. But here's the craziest part. Hantavirus does not actually kill the cells it infects. It is not cytopathic. Instead, it uses a complex strategy to hide and keep the cell alive. The virus's N protein and G1 protein act like stealth cloaks. They bind to human immune proteins and prevent the cell from sending out the chemical alarm bell that warns the rest of the body of an infection. The virus also activates survival genes in the host cell, which explicitly prevent the cell from dying. Because the virus isn't killing the cells, the damage to the human body actually comes from our over-enthusiastic immune system. Our white blood cells get incredibly frustrated. The infected cells start releasing cytokines, like CCL5, which call in a massive swarm of immune effector cells. As these immune cells aggressively traffic through the walls of our blood vessels to reach the infection, they damage the delicate endothelial layer. This creates the blood vessels to become leaky. Fluid spills out of the bloodstream directly into the lungs, in HPS, or damage the kidneys, in HFRS. You essentially drown in your own fluids because of friendly fire from your immune system. If 2 different hantaviruses infect the exact same animal, they can swap their genetic segments, creating a brand new chimeric virus with novel characteristics. In lab studies, researchers proved that the Sin Nombre virus and the Andes virus can easily swap their medium segments, meaning nature is constantly rolling the dice on new, potential more infectious strains. Because the early symptoms of hantavirus mimic the flu or COVID, diagnosis is incredibly difficult in the first 72 hours. If doctors suspect a case, they can use testing, or RT-PCR, to hunt for viral RNA. Because patient blood samples are a severe biohazard, they must be handled under maximum biological containment conditions. If you test positive, the options are limited. There is no specific approved antiviral treatment or vaccine for HPS. An antiviral drug called ribavirin has shown some success against the kidney-focused HFRS, but it does absolutely nothing for HPS. Instead, doctors rely entirely on aggressive supportive care. Patients are rushed to an intensive care unit. For HPS, this means mechanical ventilation to force oxygen into fluid-filled lungs, careful control of fluid volumes, and sometimes extracorporeal membrane oxygenation, ECMO, a machine that literally pumps your blood outside your body to oxygenate it. For HFRS, patients might require dialysis to filter their blood when their kidneys shut down. Because doctors can't be sure it isn't a bacterial infection at first, broad-spectrum antibiotics are often given empirically. The best cure is prevention, and that means keeping away from rodents. Seal up gaps in your home, use traps, and secure your food. If you find a rodent infestation, never use a vacuum or dry sweep with a broom, because that kicks the deadly viral particles directly into the air you breathe. Instead, thoroughly dampen the area with safe cleaning chemicals or bleach first, and use wet cleaning methods alongside strict hand hygiene. Healthcare workers must use standard precautions, upgrade to airborne precautions like specialized masks, for aerosol-generating medical procedures. As for the cruise ship, by May 4th, there were a total of 7 cases, 3 dead, 1 critical, and 3 suspected cases with mild symptoms who isolated in their cabins. Health groups stepped in to support clinical management and medical evaluations. Laboratory samples were flown to Senegal for sequencing and metagenomics. Despite the tragedy, the World Health Organization assessed the risk to be global population as low. They advised against any travel or trade restrictions, emphasizing that most routine tourism carries little to no risk of exposure to rodent. The passengers simply had the terrible misfortune of likely encountering rodent habitats in South America before boarding. It is a stark reminder that as we continue to push into the natural world, we are surrounded by invisible biological machinery. Machinery that, if given the chance, can turn our own bodies against us. If you liked this video or found it helpful, subscribe for more. I make all content surrounding biology. If you want something more exciting or creative, check out my last video, What is Astrophage? From Project Hail Mary. That one was more fun and uplifting than making this video. But anyway, thanks for watching.